Thank you. So today I'm just going to give you a very broad overview for this technique that we have started to use here at the CBU. So at the moment we're in the middle of piloting this technique, both in the MEG, EEG and separately with the fMRI. But the reason I wanted to talk to you about it today is because I think it's got quite a broad application for lots of different domains and different methods. So just for an overview of what I'm going to talk about today, I'm going to give you the background as to what actually is the fast visual periodic stimulation paradigm, and then I'm going to give you some examples of how it's been used both in healthy participants in EEG, in patients using ECOG, and some preliminary work with fMRI. So the paradigm has been developed extensively over the past 5 years or so by Bruno Rosillon, and it's a variation of the widely used steady-state visual evoked potential paradigm. So for those of you who aren't too familiar with this, the steady-state paradigm involves presenting visual stimuli at a particular frequency, and this results in neural responses at the same frequency that they were presented at. And this can obviously be measured with EEG or ECOG. So the way that the fast periodic paradigm goes beyond this is to incorporate what they call oddball conditions within that train of images. So you incorporate your condition of interest that repeat at a slower frequency within the periodic train. So just to give you a picture of what this looks like, if you imagine that we have this train of images, and these images are appearing at a frequency of 6 Hertz. So each one is appearing for about 170 milliseconds. And within that train, you see 4 pictures of common objects, and then the 5th image is a picture of a face. And then you'll see another 4 objects, and then another face, and so on until the end. So each of the stimuli are appearing at 6 Hertz, but within that, the face images are appearing at a frequency of about 2 Hertz, so at a slower frequency. And the idea is that we can measure where in the brain is responding both to the base frequency and to that selective frequency. So just to give you a better idea of what it looks like, I've just got a short video of that paradigm. So it looks like this. The stimuli appear modulated, so they don't appear as very flashing on the screen. And the instructions that participants are given are very minimal. So they're just told you're going to see some images, just watch the fixation cross. And when you see the fixation cross change colour, just press the button. So it's a very simple task and minimal instructions. And the nice thing about this is that you can get a lot of high quality temporal resolution data with very short acquisition time. So this experiment, each of those videos lasts for about 60 seconds. So it's quite it's good for use in populations who either can't sit for long periods of time, like patients, or in children who might not be able to attend very well, but also in healthy participants as well. So just to show you the results from that experiment, so I just showed you the periodic condition there. So this is involving the 6 Hertz train with the face stimuli appearing every 5th image. And then they also contrasted this with a non-periodic condition, so it's the same images appearing. The only difference is that the faces appear randomly throughout the train of images. And then this is also contrasted with a scrambled condition. So here the scrambled pictures are the same images in the periodic train. They're just phase scrambled, so you can't get any semantic information from them. And this was a study that was run in healthy participants using EEG. So I'm showing you the results from 2 electrodes. So there's an electrode over OZ, which is in the light colour here, and then from PO8, which is on the more lateral occipital surface. And this is just showing you frequency along the x-axis and then the amplitude plot here. So you can see that there's a very defined peak at 6 Hertz, which is the base frequency that these stimuli were presented at. and this is strongest in OZ, which you can see on the topography map there. So the idea is to then see if you get additional responses when you have the periodic condition versus these, the non-periodic ones. And these are the results from this non-periodic condition. Again, you can see this peak at 6 Hertz, but this time the topography of the responses changes. So instead of being this kind of medial occipital regions, you start seeing more lateral occipital regions when the pictures have meaning versus seeing just scrambled pictures. And then when you look at this periodic train, so where you have the slower repetitions of the faces appearing within that train, you again see the 6 Hertz response to the base frequency, but you start seeing these face selective responses at 1.2 Hertz, and then the harmonics for each of those responses. So this was kind of a proof of principle that there is something measurable within this periodic train of images. So this whole experiment, each of these conditions were repeated 4 times, and each run was a minute long, so they got all this data in about 12 minutes of EEG. And then what they wanted, most of the research in this area has been done in the context of object processing and face perception. So more recently, Bruno and colleagues have been trying to extend this technique to other kinds of stimuli. So they've been doing it with written words as well. So this is just showing you a video where you see real words embedded in kind of pseudo fonts, kind of like scrambled word type images. So the idea is the same. You see each image appearing for 100 milliseconds. So here the base frequency is 10 Hertz, so a little bit quicker than the pictures. And the words repeat every 2 Hertz. So every 4 images you see a real word. But the task is the same, and you can collect this data within about 70 seconds of testing. And then they showed that you get responses to the oddball word stimuli within the left occipitotemporal region. So it's not only restricted to using picture stimuli, you can start kind of probing more lexical type of processing. So most of these effects have been probed quite extensively. So they've been tested in terms of their robustness to things like low-level manipulations of the images, so they can replicate inversion effects for faces, and the effects disappear when you negate contrast. They're also robust to things like attention and the temporal predictability of the stimuli and the repetition of the stimuli. There's a whole host of literature on kind of the drilling down into the methods of this, so if anyone wants any of the references, just let me know. But one of the strengths for this technique is we think it lends itself quite well to populations where people can't, so patient populations, for example, where they can't deal with very intense task demands or sit for long periods of time. So I'll just show you a couple of examples where this method's been applied to ECOG data in patients undergoing awake surgical mapping, like we just heard about. So these data were collected in the bedside ECOG data, and they're using the exact same task as I showed you at the beginning with the objects and the faces, but this time they're measuring from individual electrodes placed directly on the cortex of the patients. And similarly to what they found in healthy participants using EEG, you also see these periodic responses. So this plot here is just showing you from one example from one patient in this electrode here, which is in the posterior fusiform gyrus. And in the non-periodic condition, where the faces don't repeat at equally spaced intervals, you still see the base response at 6 Hertz, but you don't see any other responses. And that's in contrast to the periodic condition, where you start seeing these face selective responses at 1.2 Hertz, and then the following harmonics after that. And you can get this group map of activation. So each of these circles represents one point in all the patients that were tested, and the coloured ones are the ones that showed this phase selective frequency response, with the red colours indicating the highest amplitude of responses. So you can build up like this whole brain map of where is responding to a particular type of stimulus. And you can also do this with the word stimuli. So again, this is a plot in one patient, this time in the left posterior fusiform, and you can see the harmonic responses to the words that we're repeating at 2 Hertz as well. And you can build up a similar map of where responds to words embedded in different types of stimuli. And finally, just in the last couple of minutes, I'd just like to show you how they've been extending this technique into fMRI. So obviously with EEG and ECOG we get very good temporal resolution in the data, but we lack the spatial sensitivity, and that's where fMRI comes in. So for this technique, the focus is not on finding the specific timing of the responses, but it's all about trying to make the stimuli appear more natural when viewing. So in standard fMRI localizers, you tend to see a block of objects, for example, followed by a block of faces, and they're presented quite slowly in a way that's not very natural to the way we normally view scenes in our environment. So the idea behind this technique is to make the stimuli that you see in the scanner a bit more natural. So you see these kind of natural images. So this is showing you the timeline of the stimuli, and each of these bars is one image. So the blue bars are the non-target category, so objects, and then you start seeing these mini bursts of the target category, so those are the faces. So rather than just seeing a train of objects with one target image, they now have mini bursts to try and simulate a more block design type of experiment in fMRI. And again, just to show you what this looks like, so it's very similar to the EEG. So the base frequency again is 6 Hertz, and then every 9 seconds you'll start seeing the interleave repetition of the faces amongst the block images, and then you can look at those mini blocks of stimuli. And again, the task is just look for the fixation cross, and when it changes colour, press the button. Okay. And within this study that was published in this past year, they've compared this fast periodic approach to a more conventional face localizer to see do you get increased SNR in the face selective regions when you use this periodic stimulation approach. So this is just showing you the whole brain results using a conventional on-off face localizer. So you see activation on the ventral posterior fusiform, posterior SDS, and early visual areas. And this is just in comparison to the periodic condition. So I'd just like you to take away from this slide that you get the same brain areas, but you get higher values across the network of regions, and you also start seeing areas that are a little bit more problematic to image, as we heard this morning from AJ. So this is kind of a proof of principle study that this technique might be useful for fMRI, and part of what we are doing at the moment is just try and extend this and replicate these results, but using combination with more multi-echo acquisition, and try and explore the fMRI, the usefulness of fMRI with this technique alongside the EEG results. So just to summarise, so the fast periodic visual stimulation paradigm is a modified version of the widely used steady states paradigm. It's got a number of advantages in that it can be applied to multiple imaging modalities in multiple populations, so both healthy participants and patient populations, and they've also started using this in children, developmental studies as well. So the data can be acquired very quickly, in as quickly as 1 minute per run, and you get good SNR even with the short acquisition time. So, as I say, we're openly piloting this at the CBU at the moment. And what we want to do is to be able to extend this method beyond kind of the perceptual processing domain and into more higher order cognition, including semantics, and see if we can manipulate the types of probes that are used and the distance to the targets and things like that. And we also want to see if we can extend it to use multimodal stimuli. So rather than having just a train of pictures or a train of words, can we alternate between the two and kind of capture more multimodal processing? And we're doing this both in fMRI and with MEG, EEG. So just finally, if anyone would like to have a play around with this, there are some freely available scripts that are written in PsychoPy that are available on GitHub. We've been using these in our piloting, and they're very simple to use and quite easy to switch stimuli in and out. And I'd just like to thank Olaf and Matt and Edvin for helping us with that MEG triggers, and you for listening.